We've spoken a bit about hardware, about NUMA, about all the things you can get. I think what I'm trying to convince you about here is that tuning is an exact science. All the information you need is there. There's a lot of places where you can go to get this. There's a lot of interpretation about it. I want to try and go, unless you want to dig in even more about how to do this, but I think one of the things I want to also get across is say, okay, when you're coming from the other side of the equation, when you're coming from the, I don't want to know about the hardware, let me just create something that works as far as I can go. Now, I'm generally opposed to best practices. Best practices are normally better than nothing, but they are also very dangerous, because if you just follow best practices, you may conclude that you've done something right without analyzing the problem. So I'm not a big fan of best practices like that. But I will give you some ideas about what works, what I've seen work a lot, and what I know doesn't work, and what I've seen fail a lot. So there are some patterns that you can use in your exploration of scalability. So I want to jump to data modeling and come a little bit from the other side, and we can sort of build the bridge between them as we go along to give you some idea of what's going on here. To do that, if we look here, and why is the default of PowerPoint not to start from the slide that's highlighted? Oh, sorry. There we go there. There we go. So if we look at basically going all the way from the hardware up through the PCI bus into the database, what we eventually end up with is the data model. The message about hardware is today, all of this is not your problem anymore. If you build hardware right, you do not have bottlenecks anymore. It's perfectly possible to build a system without bottlenecks. They're cheap too. The responsibility of creating scale increasingly moves up here to the data model. To take advantage of all these things. To understand that synchronization and the way to partition data loads is going to be the important part in the future. And it means that we see a new player on this market, which changes the picture quite significantly. So this is an illustration from my blog. Don't worry about the arrow numbers there. That's not so important. This is an illustration from my blog about my recommended approach to data warehousing, the approach that I've seen work. And you'll see that there's a little hybrid between an elephant and a bee here. That's the new big kid in town. There's something called big data out there now. And when people define big, they're sort of a little bit, some say it's petabyte and some say it's 10 terabytes. And that's not really the point about big data. The point about big data is it's a way to store data in a way that's truly cheap. Not cheap as in sand cheap, or cheap as in direct attached storage cheap, but cheap as in I'm just going to keep adding machines that has storage to this. The failure unit is a machine, and I can just create an unlimited large file system. So it's the ultimate dump site. You can just dump all your data there, and it's truly cheap. The cost per gigabyte is very, very low on these systems, much lower than anything you can build with a hardware vendor. What big data gives you, apart from a massively distributed, highly available file system, is it gives you a way to curate that file system. But the beauty of that is you don't actually need to have any structure in your files. You can just sort of throw them into a pile. If you have CSV files, you can put them there. You can put tables in there. You have different storage formats. You can free text index them. It's the stovepipe of all stovepipes. So it's a good way to work around a common complaint that I hear a lot. If you go to a business user and you try to have an intelligent conversation with them about things like, so you have this OLTP system with all your transactions from, let's say, your supermarket. You have all your transactions from your supermarket here, and then this OLTP system. And I want to put them in the data warehouse, and I want to analyze them in the warehouse. So first of all, they'll ask you why they need to store the data twice. And you can have a talk about why you don't want to disturb the operational system and why it's expensive to join. Once you convince them that they need a warehouse, the next conversation you need to have is, so given that I'm storing your data, how many years do you want to store? It says, oh, we'll be open for 10 years. Yeah, but how many years do you want to store? Well, 10 years, obviously. So when can I throw the data away? And what is the answer always to that question? Never, right? Because nobody wants to throw data away. Data is so rare that you get the chance to actually get rid of data. until you start putting a price tag on it, and then you can have a conversation about it. But if you just talk about from a pure design perspective, people don't throw data away. That just doesn't happen. Data is too valuable, or at least it's perceived to be too valuable. What these Hive, Hadoop, big data type systems allow you to do is they allow you to take that conversation off the table and say, here's a cheap storage, and it truly is cheap. No, you're not going to run it on your SAN. No, you're not going to run it on your special servers. You're going to go and buy the cheapest hardware you can find. You're going to shove it full of SATA drives, and you're going to find some cheap network switches, and you're going to stuff it all into this box, because that's the way Google runs it. And it's going to be okay. It won't get lost, and you can take backups of it, and it'll have double. And all of that data you don't know if you're going to use and you're afraid to throw away, you put it in there. And no, don't bother modeling it. Too much work. Just put it in there. You can take that conversation off the table now, because you can truly create cheap storage with this. And it also allows you to explore the storage if you're in the fortunate situation that somebody actually can run queries on top of unstructured data and just sort of look for new theories. What it doesn't allow you to do is it doesn't allow you to do a mass distribution of data. That's not what it does. It allows you to create theories on data, and they're working on making it mass distributable. But at the moment, think of it as an exploratory area. To do that, you still need warehousing. Warehousing is about the mass distribution, the normalization of data, and I don't mean that in a relational sense, but the creation of data sources that people trust, that are structured in such a way that you can run your organization on. You'll typically have some staging, and you'll get into some tables here, and I'll get into what that means, what those tables are all about, and get into the flow of that. So basically, you stage the data. This is sort of like a throwaway database. Here's your enterprise data warehouse, and you might even have some marts on top of that. And at the end of that, you give it to a user. You will have noticed that I write the word fact in here, because I don't believe that there's any form of enterprise data warehousing that does not include a dimensional modeling. I believe that fundamentally Inman is wrong, and I'm going to get into why. What is it that isn't in this organization? So there's a lot of these things that people argue should exist, like ODSs, for example. Sometimes ODSs can be nice. They can be replicas. You have something called Data Vault, which is the new big thing. It's basically take normalization to an extreme degree. I don't know why people want to bother doing that. You can have archives and all that stuff. All of that is sort of gone in this architecture. You don't have an archive. You don't have an ODS in this architecture. All of these have sort of different definitions too, depending on who you speak to. The nice thing about having a copy of all your source data is, and this is a very big driver for EDW, is that you can reverse choices. You will never get a business user, or you very rarely will get a business user, to agree to making a choice that includes throwing away data. That's very rare. You say, which columns can you live without? None of them. Right, so the right way to ask, if you have a table and you want to give that table to a business user, the right way is not to give him a list of the columns in the table and then ask him to check the one he wants, because the answer will always be all of them. The right way to pose that question is to say, which data do you want? And then I'll try to find it in the table. That way you can limit his choices. You don't want to give business users too much choice unless you really trust them to truly be conservative about this. So the idea of having this semi-permanent storage is good in the sense that the source systems may throw data away because they have to. OLTP systems have to get rid of their data at some point because they just can't continue to scale a lot of them. And SAP don't create super large databases. There might be 10 terabytes out there, but they're not going to store 100 terabytes. They're going to throw it away. They're going to put it into a data warehouse. We need something where we can store that data that so nobody else will guarantee us is always there. If you can have a conversation with the OLTP DBA and say, OLTP DBA, can you please guarantee me that you will never throw away data? Don't bother storing it. Could you sign here on the dotted line that you won't throw it away so that when I need it in the future, I can always come and get it? You can get him to do that. Why bother having your own archive? Just take a copy of his data. And it allows us to do something interesting with this semi-permanent storage. It allows us to do what I call replay of the source. It allows us to take our ETL code, which is the true transformation code we have, the one that actually decides what our data model is, and change that code and replay the system. This is a big claim here. What does that mean to replay? It means that if you design your warehouse in such a way that it loads very fast, you can take your entire warehouse and completely rebuild it over a weekend even if you have 100 terabytes of data. If that was your world, would you bother modeling all that data that you're not going to use? If you could truly move data around, and I'm telling you, you can, you don't want to model. You don't want to model all that stuff. You just want to spool it forward and say, actually, I completely want my fact table to be a different structure. Let me change the structure of my fact table. First of all, you have to deal with all the report users that will be screaming when you do that. But assuming you could do it, you just fast forward again. You load your data from the raw format you originally received it in coming out of your big data system, and you now have a new structure. And your ETL load can be designed to be highly parallel, and you can do this. I mean, 100 gigabyte data warehouses are trivial to reload if you do loading right. And this is one of my points about data warehousing. If you're modeling the source, you're wasting your time, because you already did model the source. You have ETL code. ETL code is a model of the source. It's code that understands how to take something that comes from the source and turn it into something you want. This intermediate idea of putting it into some third normal form and storing it twice in something that's super normalized because Inman told you that that's the way you should do it. Why? There's no information in there that isn't already in detail. Now that's a big claim. Let's look at some things you can do to make this an easy task. We have the staging. I think of it as sort of like a big TempDB. Sometimes we know that having an intermediate result stored on disk, because we can't hold it in memory, is a good idea. That's why we need some temp space. For example, if we want to sort a very large data set, sorting in memory is not always possible. We may need to store it on disk, we may need to build an index on it, we may need to sort it. Staging is a good tip for that. Staging also helps us to store intermediate results that help us with debugging if something should fail, or help us restart from the last point of our ETL. So it sort of us all, and then another thing that it does, it allows us that if the source needs to get the data out, we can just get it out, disconnect from the source. Minimum interruption of the source. So staging is sort of our scratch pad area. The way I think about staging is the database you can, if you drop that database, you won't be crying. Just create it again next day. Then the question now becomes, if you're an Inman world, your world looks like this. You have an EDW in here, and depending on which of Inman's book you read, he seems to have gotten wiser as he grew older. This may be third normal form, or something else. If you're Dan Lindstedt, this is data vault, right? It's some academically very complicated, logical, physical, Irvin implemented thing in the middle, right? And you pay a consulting house a lot of money, more money than you spend on the hardware to build it. Anyone you've been in a data warehouse like that? Because I've seen a lot of them. And the one thing I can tell you about them is that almost every one of them fail. And then there's the Kimball model that says, actually, let's be a little bit more pragmatic about our world. Maybe we'll just deliver data marts to the business units in the way that they need them. And we might have something here in the middle that sort of looks the same. But fundamentally, what this is all about is star schemas. I hope we agree that in order to present information to the end users, the vast majority of times you need a star schema, because that's what users understand. They understand dimensions, they understand facts. You can show it to them in client tools. There are cases where you want something that's more normalized, but most of the cases what you want out there looks a lot like a cube. So those are sort of the two paradigms that are fighting each other out there in the warehouse field. And depending on which religion you swear by, and you should be quite obvious by now which one I do, you will argue for one or the other. But let's look at some numbers. This is sort of what it looks like. Actually, let me just tell you about what I call the Inman trap first. The Inman trap is this. First, you overplan the EDW. Because if you're Inman, you believe that you have to have one model to rule them all. It's a company-wide effort, heroic. And we will push it down, and I don't know, I work in a big company. I've never seen anyone push any heroic efforts down from the top. But that's what they believe. So you need one model. Now, just because you want one version of the truth doesn't mean you need one model of the truth. These two things are not equivalent. So you say one version of the truth means that you need one database. This leads to the next logical step. And I realize that I may be undermining our PDW sales now. you start evaluating these enormous database requirements because you sum up all the data that you have in your entire organization, and you get a big number because most organizations have a lot of data. And what you want to is you want to make a capital investment that you can protect. And to do that, you need something that's dynamically, flexibly scalable. Enter Oracle salesman. Teradata, PDW. Right. You don't have to worry about how much data you have because if you fill it up, you'll just buy more. Right. Any of you been in that one? I've seen 2 terabyte warehouses be in this situation, right? Desperately trying to think out what would happen if they become 4 terabytes. If you become 4 terabytes, you spend another $20,000. And now you have 4 terabytes, right? And your total warehouse budget is $1 million. I think we can survive buying a server. Right. This happens. It happens a lot, unfortunately. And of course, you want to do it sort of, you need to protect your investment. And I realized there are organizational reasons why this happens, right? There are good reasons why when you put in that budget allowance, you're not going to ask for another one. And then you go to step 2, if you think that that might be silly, when you start getting the consulting bill. And then you sort of go in this. This is surprisingly common. I'll tell you a story. This is a real story from a major bank. For some reason, banks like to do this a lot. I don't know, something about banks. We came into this bank, 2 CAT members, and we were talking about the data model. And very soon it shall become obvious that we're not consultants, because then we wouldn't have said what we said. And they come into the room and they hired this expensive company that spent 300,000 euros on building a data model. So we already spend more money than we normally spend on one of these small-scale data warehouses. And he comes in with this, you know these printouts you get from A1 plotters? I call them parking lot models. And everyone gathers around the table, and there's the big one here, right? I was looking for, I actually have that illustration taken sort of long, anonymized properly. And everyone gathers around the table. We start looking, oh, that's a big table. That must be a fact table over there. There's one big there over there. We start sort of exploring and asking the big questions. So what's that? And then in comes another consultant. And he's not carrying one of them. He's carrying many of these drawings, right? And the guy over here at the table just says, yeah, that's the customer dimension. Right, so these guys spent 300,000 euros modeling a customer dimension that they might use one day because there wasn't a single attribute in that dimension that they hadn't super normalized and created into something that they might come in handy, because you never know what business requirement you're getting, so we better spend the money up front. And then in came the other ones. Product dimension. Store dimension. 5 years later, repeat, and we exited the loop, found a new CIO. And we redesigned the data warehouse in a few months. This happens a lot. Very often this is about the fear of losing data. And I understand why this happens. It happens because you're afraid of designing something that isn't flexible. And if we have agreed up front that we're going to buy the cheapest storage we can find, that is still highly redundant, that still works, so that we are never going to lose our data, and we have agreed up front that we designed our data loading in such a way that we can load literally at gigabytes per second, which you can do for cheap money today, you're in a situation where we can always recover. If we decide that we needed that attribute in the dimension and it wasn't there, we can build it. There are some tweaks we need to do to the Kimball technique in order to make that fully flexible and make sure that it supports our requirements. But we have an option now to get back to previous design requirements and repeat our loaders and try new things. The versioning is no longer a versioning. We don't need a data model that's ultimately flexible, because that leads down a path of madness. Instead we get ETL that's ultimately flexible, which is code. We can version code. If we want an older version of the warehouse, we can rerun an older version of the ETL, because we check our ETL in the source safe, don't we? When you do this, you do, because now you start thinking of ETL as code. Code that generates the final data model. The fact that it has a staging in between, that's nice. But all of the data is there. You can get back to it if you want. This means that we need to look a little bit at where time goes. We spend quite a lot, so this is sort of a typical pie. Dimension load is trivial. If you can't load a billion row dimension, that's type 2 or type 1, I don't care, in a relational source, I'm not saying a cube. Thomas is sitting down there. If you can't load that in less than half an hour, there's something you can improve. Don't use the integration services dimension method, please. It's really bad. But if you write your own dimension loader, you can generally load very large dimensions very fast. So dimension load, I would claim, is a very small part of the pie. Dimension load is trivial. It's complex from a coding perspective, but it's trivial from a load perspective. Aggregation is rather expensive, actually. If you want to aggregate a data mart, that's actually expensive because it typically involves sorting, and sorting is expensive. But by far, the largest cost of a data warehouse load is the green one here, which is loading the fact table keys. Coming up with something that's in the source system because it's practical for the source system to have character keys with obscure German names in it, with encrypted data, because we don't want people looking at our data model. Just an example. So they come out of there. You need to do some key lookup. You need to compress them a little. And all of that is really expensive. A lot of CPU is spent doing this. So it is our interest, if we want to design something that loads fast and that is maximally reusable, so that we can reload things very fast, it's our interest to reduce this, to only pay this price once or pay a few times. So we need a data model that is flexible with respect to this. This means we need to have a talk about what keys are. Now, I blogged about this extensively. If you want to see some performance numbers, there are some of those on my blog. But these are the characteristics of the key. First of all, it's small. Secondly, it's an integer. And the reason it's an integer, the reason that you don't store currency as character free, you may do that, but the reason that it's faster to store it as an integer is because integers happen to be the units that CPUs actually work with. If you do column stores, you'll get some help there, and we'll talk about column stores later. Once a key is assigned, it doesn't change. Keys don't change. If not, they're not good keys. This, by the way, is true for OLTP modelers too, if you're going to build one from scratch. It does raise the question about what an entity is. So there's a design question you have to make here. What is an entity? Right? An entity is not something that has two different versions of history is still one entity. We'll get into that. So if you have a product and it changes its characteristics, it's still one entity. Notice that Kimball doesn't make that distinction. Kimball says, I need a surrogate key because it's great. It's true, it's great. It's small, it has this property, and it has this property. That's the Kimball argument for the surrogate key. But there's actually two things going on here. One is that it's optimal from a compute cycle perspective. But the second thing Kimball does is he also has the surrogate key to capture history. That's why we have type 2 dimensions. We can create. Is anyone familiar? Anyone here want me to dig into what a type 2 dimension is? Everyone's familiar with the concept? Yeah, okay. So that's why we have, so it serves two purposes. It serves the purpose of being computationally smart, and it serves the purpose of having history. We don't want to reuse these ones, which means it has to be big enough for that to be the case. And this is very important. It's stupid, or Teflon, nothing sticks to it. It doesn't know anything about the thing it refers to. And the reason it doesn't know that is that the moment we let the key contain information that is usable by an end user, that end user might start creating reports that refer to that key. And the moment the user does that, we lose our ability to change our model. Because now there are hard-coded references to a key that has no meaning in there. Now, the one exception to this is, of course, the date time. I would claim that time and date doesn't change. Right? Date, time is what it is. And that follows that it shouldn't be remembered by users. When users start referring to our keys directly, we're in trouble. It is much preferable that they join to the table and use the joins to get it there. And we will see how column stores help us achieve some of these goals. Because they actually, when things look like this in your column store, you're lightning fast. Okay. Let's see. here's the problem with the surrogate keys. The first realization is source systems don't provide good keys. I mean, have you seen a source system that provides good keys? I haven't. I mean, source systems just do crazy things, right? Some user runs out of keys because it's a mainframe. They have a character 4 down there, which is in some obscure IPsec encryption, probably too. And then they run out of. So the classic example is bank codes in Denmark, right? In Denmark, the first 4 digits of your credit card is the bank code. Guess what? There are more than 10,000 banks in Denmark. So they start reusing them, right? They get into some elaborate schemes where the keys are sort of recycled. And you get into some really odd data models. There's a history on the key, and you have to join on the history. And source systems do crazy things. So it's generally a good idea to not rely on the source system to supply us with a key that we can trust. And again, so you're saying your key has these properties that I just gave you? You sign here, please. So that when I model on top of it, it's not my problem anymore. So there's different sort of. I've got a blog called The Pathology of Source System Keys. That describes different types of them. Zombie keys that rise from the dead because they mean something else when they do. And sheep keys, dolly clone sheep keys and stuff like that. There's a whole taxonomy of it, and you need to analyze that. You need to understand how the source system generates keys, but don't use them just because you understand the keys. It's generally a good idea to create your own. So if we don't trust the source system, that's just a basic assumption. So basically, do not rely on that. And the other problem with surrogate keys is that they have this odd property that they can change. Surrogate keys are actually not good keys. They're small and they're integers. Great, that's a good key. Unfortunately, they also track history. So here's a classic example of a dimension of customers, let's say, and here's me. And somebody decides they want to change their business requirements. Actually, they want to track my education too. They got access to that data somehow. When that happens, the dimension changes. And when the dimension changes, this results in what I call a mega update of the fact. So all of that work we did with all the key assignment of the facts, now suddenly we have to reverse that work. That could be quite expensive. So surrogate keys have this sort of nasty feature about them that if we change our mind, our facts change. So surrogate keys aren't just all happiness. And for some reason, what can we do about it? One way to do about it is that there's such a thing as an entity. Thomas doesn't change. Somebody clones people at some point. So there's an entity, and we can take the type 2 columns and we can put them in a separate table. We can normalize them into a separate table. And then we can take the type 1 columns and put them into the fact table. Now we're not changing anymore, unless an entity completely disappears from the planet, or clones, or we discover we had a data error. But that's typically a much smaller problem than changing our mind about history. Data errors can be corrected with simple update statements. Of course, now we need the valid to and valid from out here in our history table. And this gives us a bit of a problem when we want to reconstruct a type 2 dimension out of this. Because we now have to do this between join. If you are a third normal form Inman data warehouse, you probably run into this problem, where you try to track history of everything, and because you normalized everything, you also realize that you have to shard things out. If your data vault, you'll have this problem because you'll use satellites and hubs. So hubs is this one, the satellite is this one out here, and you'll discover that this quickly becomes very, very complex. But it especially becomes complex if you haven't in advance decided that you're star schema. If this chain is very, very long, imagine that join. And it becomes complex for a lot of reasons. Let me show you one of the big ones. What's this going to do to the optimizer? What is it going to do when I try to join this product up here to get this here? How does the optimizer know that there's only one key that matches that join? It doesn't. as I crawl, if I decided to snowflake, and I'd crawl into this tree further, or if I'm third normal forms of this one, forbid it, would be normalized too, line items and orders, then that becomes very complex very fast. The optimizer won't deal with this. You can wish for optimal optimizers, but you're not going to get them. They don't exist. So what you typically end up with is, if you haven't decided that this is a star schema that happens to have this sort of little type 2 dimension falling off it, those joins, reconstructing the type 2 dimension becomes very expensive. So you definitely want to be careful about that. Very often you have to hint it. There's another little thing about this, is that when you do this, the only strategy that is useful is a join, an inner loop join, not a hash join. Loop joins are much slower. Hash joins are our friends in warehouses. So you might want to store it like this in the warehouse, but you don't want to give this to your users. If users start playing around with joins like this, you'll get a slap on your wrist on performance. This is not a good way to give the end user a good performance experience. This leads me to another reason why Inmon is bad. Let's say that we model like this instead. Right, so we have some ID there, we have some from, to, and things are just modeled. There's no star schema, it's just there. It's third normal form. Every table is the same. So here's our business user. So he said, give me a type 2 dimension, because I want a dimension. I'm a business user. I don't use third normal form things. Give me a type 2 dimension that tracks A, B, and C, but not D. So give me a table that has a new row for every time one of those three changes. I don't know about you, but I don't feel comfortable writing that join. Can you write that join? Can you hire a consultant to write that join? Can you scale, and by this I mean organizationally scale, the effort required to reconstruct a star schema out of this? I've seen query plans with 70 joins in them trying to do this, coming back to me and say, SQL Server is broken, it doesn't scale. I say, no sir, you are broken. So that's another good reason, is history tracking. If you decide to model history tracking in the most generic way possible, in front, before you even start thinking about business requirements, you have already shot yourself in the foot. If you create models that look like that, no one will be able to maintain them anymore. That's why you just need to shove all that history into some source system and then reload your history in those cases. And if you did what I just described here, you can shard off new histories as you want, while remaining the expensive part, remember, was to generate this table. All of the loading and the joining and creating this table out of this and assigning integer keys, all the benefits that you harvest, you can still harvest by modeling like this. This one is small, it has all the good properties that a Kimball table has. And it has flexible history tracking. So you can create a data mart out of this one really fast. So it has the properties you want it to have without falling into the Inman trap. All right. So ETL solves the history problem. History tracking is a part of your end user data model. It's not part of your previous model. It's not part of that thing in the middle, if there even is a thing in the middle. And this leads me to what I think is a very key insight for data model. It's very easy to load an Inman schema. If you're building a data vault, it's even easier to load a data vault. Data vault is a great technique for loading something very fast. It's a horrible technique for getting data out of it again. Data warehouses are not about loading data. They're about getting data out. So just because it's easy to create a data model that's easy to load doesn't mean it's a good data model, because data models are about responding to user queries. So model after that. That's my recommendation on doing this. And this leads me to column stores.
Yeah, Just one thing, Thomas. I don't know if people here have heard about the data vault.
Have you not heard about it? Good. That's good.
Explain what it is.
Data vault is, think about, if you look at third normal form, and then think, some of you might have done fifth normal form modeling. That's part of the original Dayton card, fifth normal form. So data vault sort of says, if 5 is better than 3, then 7 is better than 5. So it sort of takes that and just completely takes it apart, right? So you end up with a lot of tables. And I can't find that, but I have this picture of this drawing. Right? That was a data vault model, right? Customer dimension. With like tables are this small with like 9-point Arial set in there, right? You can get into some really odd situations when you do it. It looks really elegant. It looks great, right? And we've got to give you one thing. It's super, super, super easy to load data vault. So if you just want a data model where you throw all the data into some place, data vault is great for you. Just hope you got a good consultant to take it out again. So that's sort of the idea. So this leads me very nicely down to column stores, which will be a little bit more lighthearted. And I have 50 minutes, which is almost perfect for that. Has any of you, there was one person who played with column stores. So I'll start talking about why you want column stores, and then I'll talk about what they are. And that's sort of maybe the wrong way around. You'll see. Yeah. This is an early deck. This is going to be shown at SQLbit soon. Some of this deck. So this is something that's munched up from some of the previous work we've done. So therefore, it has no name and title in it yet. Okay. So let's introduce our players, right? Here's the business guy. The business guy has a problem that he wants solved in almost every warehouse, which is he doesn't know what query he's going to ask. As a data modeler, that's a unique problem. If we're an OLTP system, we have a fair idea of what we're going to do because there's an application that asks the queries. Here's the end user. He asks the queries. Of course, that's not enough. He also wants it fast. But he wants it not only to be fast, and this is a key insight. He wants it to be predictable. Now, you may be in a situation where having the fastest response time is not always the right answer. Sometimes you just want a response time that's good enough, but always predictable. It's very often better that you take 5 seconds to do something and respond to a query than it is that you sometimes take 2 minutes, but most of the time you take 1 second. Very often it's better to have an upper limit to how fast or to how slow something can run. And that's typically something that ends up as a business requirement. On the other hand, we have our DBA, who asks the complex question, how do we actually tune for that? How do we model and tune for something that's unpredictable? Obviously, we put a star schema in the middle as our first start because it limits the amount of joining that can be done. Star schema tells us something about which query path we can take. So we've created a star schema, we've done a model, we have something that looks like that. We now get into the indexing strategies of this star schema. The problem with star schemas is that fundamentally they're not very good with indexes. Mind you, they're better than third normal form models, but they're fundamentally not very good with indexes, as you understand indexes as B-trees. So here's a classic star schema. Right? It can be generated by a cube, it can be generated by any data set. It joins the facts with some dimensions. It puts some filters on the dimensions, which limit the data. And then it groups by something and does a sum. Classic schema. Traditional data warehousing. B-tree indexes. We seek down the customer to find those ones. We seek down the product to find those ones. And we have those on the fact table, right? So we can go in there, we can go into the fact table, we can find the rows that are relevant. So now we have all the rows that match Y and all the rows that match Z. But remember, this is a fact table. It's big. By definition, it's a warehouse. So what we get now is we get a list of all the products that match what we're looking for with the values we want, plus the row identifier, or cluster key, depending on whether you clustered it or not. In order to reconstruct the query result, we have to find the place where they intersect, where both X and Y is true. To do that, we need to join those two. that turns out to be expensive. If you are on a single machine, this join happens in memory, which means that the joins are generally local. You may even be in a situation, what SQL Server will do, where it will try to split these joins between different NUMA nodes. So some subset of that join is going to run on one NUMA node. Remember, the memory is cheaper if you run locally. And some subset is going to run on another node. The NUMA node memory is, jumping to another NUMA node is typically 300 nanoseconds. Relatively short amount of time, even by CPU standards. But what if this doesn't live on the same machine? What if that fact table is sort of spread out all over your standard scale-out architecture? Now, all the rows that match this product and all the rows that match this customer have to now be transported across the network to the node that's interested in those nodes. Transporting something over the network is about at least 100 microseconds. So if you're not careful in a scale-out architecture, you're now actually going to be slower than if you were in a scale-up architecture. Because every time you need to execute joins like this, which you will have to do a lot because you're a warehouse, you're actually going to be slow. Because you need to do the shuffle operations. You need to send things back and forth over the network. You can do some streaming and some pipelining, and that will help you. And there's all sorts of smart techniques you can put in place. But at the end of the day, you're going over something that, if you're lucky, is an InfiniBand link. That's 10 gigabit. If you're doing this join locally, you're going over the local memory bus. That's 400 gigabytes per second. You better be sure that you have partitioned your data in such a way that each individual scale node is capable of joining things on its own before they need to talk to each other. So this problem doesn't magically go away because you put it in an MPP scale-out system. This is not a good way to solve this problem. Too slow. There's a better way to solve this problem. The better way is that you create a composite index on X and Y. So now you have an index on the fact table that covers both those keys from customer and the product. So basically, you both have indexed customer and product. You find all the matches in the dimension. That gives you two lists, all the IDs that match the customers and all the IDs that match the product. You cross-join those two together. That gives you all the potential ways that they can be combined. You don't know which ways they are because you haven't looked at the fact table yet. This is the cross-join. This gives you a large row. If it's small enough, it fits in memory. If it's too big, you spill to temp DB, you're dead. And then you do a seek. Now that goes through one index only. You avoid the big cross-join because you're cross-joining before you're touching the fact table, and you're getting the data out of the fact table. Does anyone see a problem with that? The size of this cross-join is a big problem. There's another problem with it, which is this is fine for this particular query. What if I wanted to store? You need another index, right? This is not good. Right? What if I wanted custom and store, and then afterwards I wanted product and store? So your DBA will react to this because you'll say, you can't manage that. This is an unmanageable problem to do. You can put aggregates in there, that will help you. But fundamentally you can't manage this. It's too difficult to index a fact table in this way. Although sometimes if you have a specific query, you can make it really fast. So what's the problem? The fact table has many columns, which basically means that there's an exponential explosion in the number of combinations. It's bigger than exponential. It's combinatorial. But typically, we only need a few of them. Fact tables tend to grow fat and wide as we change our mind about the data model, as we improve our data models, and as we learn about the business requirements. The fact table tends to grow wider and wider. So we don't actually need all of those columns. There's a structure in the fact table, and this is something we're not really making use of, right? When it's winter, bikinis sell in the Caribbean, but they don't sell in Sweden. Right? So there's a correlation here, that time is correlated with product that's correlated with customer, or customer location. So there's a certain amount of structure inside the fact table. There's a lot of correlation between the columns. That's unclear what we're actually doing with that correlation. But we're not using that. Right? There's no use of that correlation, which is really a shame, because fact tables are typically highly correlated structures. So let's talk about column store. So this is SQL Server. Think of it as an abstract representation of how SQL Server stores its data. There's our custom. And I've translated the keys into a particularly good drinking session we had. And here we are in England. So there's correlation here. I'm spending more British pounds. Christian, who lives in the States, is not spending very many British pounds, so this is rare. Normally his expenses are in US dollars. And here's Alexei, he lives in Germany. But in this case, we're sort of correlated because we're in the same location and we're drinking on the same day. Good correlation. A lot of these columns are highly correlated. What if we just gave these rows numbers? Like that. Column 1 to 7. And took them like that. And like that. And so on. So now we've done that to it. That doesn't seem very smart. So we split them up. So you could do this in relational, right? You could put it in, you could super normalize it. Cut it up into individual columns. And you would have something that looked like this. And you could reconstruct the original result by joining them together. But the interesting thing is the moment we do this, an opportunity presents itself. Because there's correlation in the columns, the beer gets bought at the same time. We can actually collapse this result by using something called run length encoding. So this column, because we are only looking at the column, that single column, we can make it smaller without necessarily having to compromise. There's no data lost here. If we do that on the entire table, we get something that's actually quite a bit smaller than the original table. So I/O reduction is always good. It's always good not to have I/Os. We can also do some other stuff. We could, for example, do things like bitmap compression. So we could say, actually, Thomas, we'll call him 1 and we'll call Alexei 2. And we can now replace these ones. So these strings, or whatever we choose them to be, now become the minimum representation. Imagine we take a chunk out of the fact table, 1 million rows as we do in SQL Server, 10 million, one of those. We changed that number a few times during the release. So let's say it's 1 million rows. We take 1 million rows out. There's probably not 1 million different values in here. Which means that we can represent this with a much, much smaller number of bits than if we were to look at the entire fact table. There would be correlation in the values, which means that we can use the minimum number of bits for each column to represent the value in that column. And then we can have a dictionary so we can reconstruct them. This allows us to squeeze down the data very significantly. That's a column store at its basic. There's some other tricks you can play where you're playing around with the sorting of the columns and all that. So we can bitpeg all of this. We can make it very small. Here's some interesting numbers from what we tried. Some of these are quite significant, right? 15:1 compressions. These are way beyond what you normally get from compression. So these are basically the uncompressed numbers there. Normally you get about factor 3 compression on a typical fact table. It's about factor 3 if you use traditional 2008 R2 or 2008 compression. This one is much better. Right? You get much more compression. Now, there are secondary indexes in the current release. So 2012 column stores will not be the primary index. You'll still have to keep the table around. You can put that on cheaper storage now. But you still need to keep the original data. There's no clustered column store index. That's just a secondary index. But notice that we've done something that quite significantly improves the way the index storage space that we need. That's good, right? But I'm still paying more storage. What do I get for that storage? Well, if you look at the columns and the query versus the throughput, we notice something interesting here. We notice that if we row compress, the scan speeds over here, as the table goes wider, it becomes more and more expensive to scan the table. The more columns we add, the more expensive it is. Whereas if we column compress, that's a constant. The speed of the query becomes a function of how many columns we ask for. It doesn't become a function of what the table looks like. That's a very, very interesting proposal, right? Because that gets us very close to what it is that we're looking for. We're looking for something that is predictable and fast. We're now predictable in the sense that if you ask for a lot of columns, it will take you longer than if you ask for a few columns. But your prediction is not going to get changed by the fact that I've changed the data model. You're still going to get the same response time, even if I make the table wider. This is great for star schema modelers, right? Because we like to make our tables wide and put a lot of stuff in there. And now we're not getting punished for it with the column store. So this is good stuff. This is predictable. But how fast is this? We need to reconstruct the column store, remember? We have these offsets that we need to join up with each other. The goal of column store is to make every query 10 times faster. That's the design goal, our design goal of column stores. Obviously, when we have less space, we need less IOPS. That's good, that helps. It doesn't help much if you're in memory, and it doesn't help much if you're very fast. It doesn't get us to 10x. But the moment we've chosen to store something in column formats, we can take a different path through the optimizer and execution engine. We don't need to be backwards compatible anymore because now we are scanning in a different way. We're scanning in something that only happens when you have column stores. We can change the way things work inside the machine. We can change our entire code structures inside SQL, which is what we did. First of all, where does these things spend time if you look at a CPU? Well, going to disk is really slow. It's like going to the moon for data. Millions. It takes forever to get to disk. Going to memory is pretty fast. Going to the level 2 caches is even faster. So if we can cram our scan algorithms into the level 2 caches, and we can sequentially access memory, it actually matters whether you access memory sequentially or randomly, so that we're constantly feeding the CPUs with a steady stream of columns. Basically we don't need to walk any pointers. There's no B tree anymore. We don't need to walk around in the pointers in memory. We can just shove the data right at the CPU and then let the CPU handle what's going on there. This is a brute force approach, but it happens to be a lot better than scanning a B tree. So if we can keep the scanning memory resting in level 2 caches, if we can optimize for the bit format that's coming in here, because we know how wide these columns are going to be, we've compressed them down, remember? We can just basically run as fast as the memory bus allows us to run, assuming that the I/O system can keep feeding the memory system. But we can basically streamline, ETL our way through the column, so to speak. In old days, we would have to go, look at this row, call out here, find the join, do this, go. That's expensive. It's expensive because it requires CPU instructions to walk all those if statements in the code. And it's expensive because it requires us to climb around in pointer trees. Say, go down this index, find the root, go to the next one, find that page, join it up again, take the next one. That's very expensive. A lot of CPU cycles are spent on that. Now, remember, if we can keep all our scans local and just to the same NUMA node, we can actually just walk through that data a lot faster. Whereas if we have to walk between all the memory structures all over the machine, all of those 300 nanoseconds we pay every time we go to one of those adds up a lot. So we're basically narrowing in our search to look, the CPU looks at the columns that it owns and the data that it owns. This is totally trashing in the old system. In the new system, we had something called batch mode, or vector mode, you'll also hear it named under. Everything fits in the level 2 cache of the CPU. The level 2 cache of the CPU basically allows us to keep the CPU busy. Whereas if we need to go to memory to find code that we need to execute, and not just data we need to work on, that costs us 100 CPU cycles every time. Going to memory for code is really expensive. We can operate a lot of things on the same column. We can basically coalesce the code into very, very highly optimized structures. And this actually means that we can bring down the number of CPU instructions we need per row quite significantly. So that's a pretty big reduction we get there. So the number of CPU instructions to look at a row becomes smaller because we can do a lot of stuff with those columns because we just assume we are brute force scanning us through them. So it's a very different way to think about it. Look at the columns you want, just go through all of them, filter them away, throw away the stuff you don't want and only return the ones that are there. It's a brute force scan. It's not a seek anymore. What we normally do when we join is we need to exchange the rows between the CPUs. So something that's scanned over here with this CPU has to be given to this CPU because that's the one that owns that join. And then this one over here has to be given to this one over here. That's the one that owns the join. It means that we are cross-talking between the CPUs all the time. So all of the CPUs are constantly throwing data back and forth over the memory bus to each other. That's very inefficient. Whereas if we're in batch mode, with column store scanning, what we can basically say is, let's start building a hash table that we will just all share. It's a read-only memory structure. The moment you mark it as read-only memory, the CPUs know that they don't need to interrupt each other in order to read the data. That structure is just going to be used for joining. And then each CPU will work on its own subset of data and just run through that data very, very fast and deliver the result. This has a very interesting side effect, and this is late in the day, so see if you're awake. If you ever tried scanning a table where, let's say, 90% of the values have one value and the rest of them are sort of distributed all over the place, you will discover something interesting. You'll discover that typically you'll have one thread executing at the end of your query. And you'll be very parallel in the beginning because we're parallelizing across all the values. But then because only 10% of the values are different, those threads will shut down. So now you scan 10% of the rows, you have one CPU basically. That CPU is scanning the last value. This means that you're now dominated by the time that CPU takes to run. Does that make sense? So if you're skewed, you actually run slower. Skew is actually typical for a fact table. You very often have skewed data. For example, if you're a retailer, certain products are much more popular than others. Like 90% of all your transactions are in those few products, whereas all the rest of them are just sort of spread all over the place. So this is a typical behavior that you typically have skew. That makes you slower in traditional joining.
Is that one of the typical causes we see these CX packet weights?
You may see CX packet weights there, yeah. CX packet may not be an indicator of a problem, but it could be an indicator where you have, for example, you have 10 threads that are scanning, 9 of them shut down, all of the ones that are no longer scanning are waiting for CX packet. So they're basically saying there's no more data for me to work on. So the typical guidance is that people say, well, it reduces your parallelism. That's not really the solution, right? Because that just makes it equally slow, right? Whereas in this case, you don't have to worry about that anymore. Interestingly, it has the opposite effect. Now, and this is the wake-up test. Can anyone tell me why it's faster to join skewed data? In this case, if you're in column store mode, joining on skewed data is faster than it's not skewed. If you have completely equal distribution, your dream scenario, that's worse for the column store. Why? I don't have any swag to give away. Would be a good one. Any guesses?
Run length encoding.
Run length encoding doesn't actually contribute here because it's faster. It's faster even if you're not even if your run length encoding is bad. It's related to the hash table. Remember what I told you about hardware and about memory being expensive? Fetching memory takes 100 CPU instructions. And our code is very optimized to fit in level 2 caches, which sit on the CPU core, which are not expensive. Those CPU caches are typically bigger than we need them to be. The chance of finding something that we need to join to in the level 2 cache is larger if you have skewed data. If 90% of all your data has one value, the chance of finding the memory in this table locally at the CPU level that you need to join is much larger than if it's randomly distributed. So that's actually pretty good because that's exactly the behavior you want in a data warehouse. So that improves you too. So what does that look like? Who reads query plans regularly? You. So query plans will look a little bit different when you do get column stores. The moment you build a column store index and you make use of it, you'll get these two new operations. One of them is the scan. That basically says, yeah, I'm scanning the column store now. I'm going after the particular columns. And the other one is the batch table hash build, which is the one that says, it's building this one. It's what comes in here. Typically, the hash build happens on the dimensions. So you hash build the dimensions and you scan the fact table. That's the general approach to a column store. So this is what it typically looks like. It works in a limited amount of scenarios in the current release. This is something that's being extended all the time. It works for hash joins, so those between joins that you put in there, you need to materialize the data mart structure. You can't do the between join. It works for hash joins only. It works for filters, where, blah, blah. It works for aggregates, of course. It's good for big scans. And it needs to run at parallelism. If you get a non-parallel plan, you won't get column store scan. There's a few things it won't work for. It won't. This one in particular is the one that worries a lot of people. It won't work for union all queries. It sometimes will, but not always. There are union all queries that won't work. GUID columns, don't use those. String filters, if you have varchars in your facts, no go if you filter on those. Numerics, this one is probably the biggest pain at the moment. There's a lot of financial applications that use these ones. So in those cases, you need to resort to things like money data types or big ints, which have similar semantics if you interpret them correctly. And also, if you're looking for a very small number of rows in the fact table, so if you're telco and you say, find me all the rows that are relevant to this particular customer. Column store is not good for that. Remember, column store is scan everything really fast. Scan everything to find one row is very inefficient. Scan everything to find a lot of rows that need to be aggregated is very efficient. So that's just something you need to be aware of. What you also need to be aware of is that your execution mode. If you get a column store plan, you will have an estimated execution mode that's called batch. That means I expect to run in column stores. That's the actual execution mode may not be batch. You can be in a situation where the actual execution mode is row. And that typically happens when you get a batch plan, but where you have some sort of memory condition that spills. So if your hash tables become too large to fit in memory, remember we rely on those hash tables to be read-only structures in memory. If they become too large, you get into a spill situation. So if you have very, very large dimensions that don't fit in memory and you don't have any way to partition them, then they will go into row mode execution. And that will be quite a lot slower than batch mode execution, typically about 10 times slower. So for column stores, they do have a sweet spot with Mr. Kimball here, which is exactly what he gets here. You need the memory. You do not want to spill those tables. It will do relatively large I/O blocks, typically 256. So it will eat some big fat disk chunks, which makes it rather friendly with disk, which means that you actually have to worry less about fragmentation when you have a column store. It's not a big deal to have fragmentation for a column store. What they actually are in the buffer pool is they're not pages, they're blobs. So column stores have a special memory manager that manages larger chunks because 8 kilobyte pages is not optimal for a column store. It needs something bigger. It needs to squeeze in a minute. Question?
It doesn't mean you can't partition align the column store indexes.
You have to partition align them.
You have to?
Yes. So column stores have to be partition aligned. You can't create a column store that's not partition aligned. And of course, the general guidance then is that you would want your partitions to be much more than 1 million rows because that's the size of a chunk. So you want some relatively fat partitions in the relational database. So that's the column stores. Sort of fine. It's fast, predictable. It saves you a lot of administration cost. It makes your data model simpler. The physical structures in your data model simply become much more manageable than you had before. So it's a big leap forward in usability. So we hope these two guys come together. But then, of course, the question is, what is the catch? What's the problem that you can get into? This is how you create them, first of all. Create non-clustered column store index. Ta-da. What we generally recommend is, if you are creating them on a fact table, create them on every column. Since it doesn't matter it's only proportional how many columns you need for your query. It doesn't matter that you put all of them in there. So just create all of them. You can only have one column store per table. You don't need anything. That's easy. Remember I told you that they come in chunks, 1 million rows at a chunk, and here the columns are stored like these. some terminology here. So you got a million columns, they contain in a row group. So we can reconstruct them into rows if we need to. And if you look at these ones, they are named segments after the analysis services terminology of the same thing. So each of these chunks of columns is called a segment. The segments are larger than they are in analysis services, which means that they would create large I/O requests. We basically store them as compressed segments, and what we have on top of these segments is what is called a segment dictionary. This has some interesting side effects. The segment dictionary basically says that what's the minimum and maximum value inside this segment of each dimension. So assume we put it in a column store and it says, well, this particular dimension, this particular segment chunk of data contains data for today and yesterday, and it contains customer numbers from 42 to 160. So they contain ranges of data that's in there. This means that because we have this dictionary that we're keeping around in memory of all the segments, we can eliminate them. We can say, well, I'm looking for data that's a week old. Well, then I don't need to look in that segment because we know that there's no data there that matches this. There's no reason to do the I/O or the memory scan. So we can actually, while column stores are brute force scans, we can actually eliminate some of the chunks so that we only scan a certain part of them. This has an interesting side effect. This means that if you build a column store on top of a clustered index that's sorted in an efficient manner, the column store becomes more efficient. Right. And why does it become more efficient? Because the segments will contain ranges that are closely clustered together. So this, for analysis services people, this has been known for some time that that's a good optimization. The same is true for the SQL engine. You build a clustered index, you sort it by something that is the least selective first, and then increasing selectivity. The opposite of what you would normally do. You would normally have most selective first and the other way around. In this case, you want the similar ones to cluster together, which means that you want to start with the least selective and then cluster them. And by clustering them together like this, you can actually get, not only do you get more efficient column stores, they also take less space. Because the segment elimination allows you to get rid of a lot of the scans, and the data itself takes less space in disk. So some interesting tricks you can gain. Here's the catch. It's read-only. You create a column store on a table, that table becomes read-only. You try to issue an insert on it, you get an error. Try to do merge, insert, delete, you'll get an error. So in order to change it, there's two ways. You can drop the column store, insert the data, and put it back on. Or you can load the data into a new partition and switch that partition in after you build the column store. That's why you need the partition aligned. So that's the catch in the current version of SQL Server. You cannot change the column store once it's there. For those of you who run data warehouses in the night, that's probably not a big deal. For those of you who have real-time warehouses,
is it still true that rebuilding a column store index is about twice as slow as rebuilding a
at least twice as slow. It's more expensive to build a column store than to build a clustered index.
But it's still true an RPM version that is about twice as slow.
I think that's optimistic. We've seen it slower than that. You want your partitions to be small enough to fit in memory. So that's one of the things. In order to efficiently build a column store, your partitions of your fact table should be small enough that you can do the sorts in memory. They can take quite a long time to build, especially as you add more data to the fact table. As it becomes wider, there's more tricks we need to play. So it's not free. You pay an insert price in order to get a very high speed selectivity.
I don't see that as a big problem now, because if we are going to create column store indexes every time and we insert data, and
yep.
if column store indexes are created on non-cluster index columns, I mean, the ranges are calculated every time. Like you said, that if you create a column store index on a clustered index,
yeah.
they're tightly, they're sorted, right? That I understand. But if it's created on a non-clustered or another column which has no index on it, column store index,
yeah.
they're still, I mean, the ranges will get redefined every time you
yeah.
create the index.
You can.
So how big is the performance difference between creating a column store index on a clustered index column versus on a column without a cluster index?
That depends on the data.
Exactly.
Yeah. So the data. So the question, whether I do it on a heap or a clustered index, essentially.
No, I'm asking from the point of view when you try to explain these things to
Yeah.
clients.
Yeah.
It depends on the data.
Well, it depends on the data,
Yeah.
right? It's the way I normally do that is if you want to. It's the same. It's the same question that if a client asks you, "How good is your compression?"
Yeah.
Well, I'm sorry. I mean, you don't know that until you try it. You can do SP estimate compression with column stores. What you can do is you can take a sample of the data and try to compress it and get some idea of it. So that's typically what we do. We just take some of the customer's data, we try to compress it, look at it. And that's the best answer you can have, and then extrapolate from there. There's unfortunately no way of knowing until you try it.
But in your experience, have you seen a big difference in performance in cluster indexes with clustered indexes versus non-clustered indexes?
We have seen more than a factor 2 speed up. It can matter. It can matter a lot. The problem with clustered indexes is that the moment you have a clustered index on the table, it becomes slower to load. So you actually take a double penalty. You take a penalty for having clustered index in place, and then you take a penalty for having the column store on top of it. Whereas a heap is really fast to load. So it's a difficult balance to take. It's that traditional weight where the more you pay for the loading, the faster your queries become. That's the sort of a typical balance you have to make in a data warehouse. And that becomes even more expensive for the column stores now. They do scale pretty well. Index creation is, I think we tested it up to degree of parallelism 48, and it's still good. Right. So if you have more cores, you can create indexes faster, assuming your I/O can keep up, of course. So you have to experiment a little with the data to get the real numbers. There's some other limitations you need to be aware of. You can't column store an indexed view. There's no such thing as filtered indexes. You can't create a non-aligned column store. You just get an error if you try. And only one for the table, but that's not such a big deal. Here's what you can do if you are a real-time warehouse, is that you can sort of partition like this, where you're loading into this, you're switching out this partition for February, you drop the column store index on it, you load it, and you create it again. So that's where partitioning really helps you. So you don't have to all of this data is locked down, it's read-only, that's fine. This is the only one you need to touch. And then you slide that out and create that read-only. So you have to come up with some sort of partitioning scheme. Thomas?
Yeah. A question here regarding comparing loading the star schema into this tabular and keeping it in the relation with the engine and put column store index on top. What about performance there when you are querying that?
Well, relational engines can use more than one thread.
Yeah.
Is that enough answer? The question, of course, is a curious. Is the in-memory BI model, once you're done loading it, faster than column stores or not? I think that's an open question. I've seen evidence both ways. I've seen rollup queries become faster than molap, and comparable with column stores in some cases. I've seen the other way too. I think that the verdict is still open. It's an open question. It is a very interesting thing, though, right? If you could keep it in the relational store, your life would be so much easier, right?
Exactly.
You could just go, wait a minute, why do I even bother doing all these cube things, right?
You have the direct query mode.
Yeah. Now, the issue with direct query mode is that have you tried playing around with that on SQL?
No. Not
Put a profiler trace on that.
yet. Okay.
And the moment you've done that, you probably want to look at rollup.
Okay.
It's direct query is still a version 1 thing, right? It's I think that it needs a bit of work to be super efficient on column stores. But it would make your life a heck of a lot easier if you could make it just relational.
Yeah.
So yeah, that's pretty much on the column store. Oh, I'm almost there with the time. So yeah, it's pretty easy to test it. You can upgrade one of your databases. Just if you already have a star schema, you're in pretty good shape to use it. Put that column store in there. Leave the other indexes in place because we can still make use of them. We can mix and match indexes and then see which queries that speed up. It's not unusual at all to see a 10x speed up. It's a pretty big change. So that was a bit about the column store. So this is available to you in SQL 11, the current.
And only enterprise, right?
Yes. have to charge you money for something. So yeah.
And developer also.
And developer, yes. So if you just want to see if it gives you a benefit, you can install a developer edition. Yeah. See if it gives you something.
I have a question. I wanted to go, if you could go back to the slide where you talked about the empty cache and why skewed data is.
Oh yeah, the join one?
Yeah, it's better.
Yeah. Let me just find that. That one, yeah.
Yeah. Conceptually, I understand why this is faster, but then in terms of getting the data, I mean, you still have to get all those million rows that may just match to one key. How does that work? Fetching, getting that skewed data is faster. Is that in order to cache?
Whiteboard time.
And it's still before 5 p.m., so we can get to
Oh yeah. Oh yeah. We can. Let me. Yeah, that's a very good question. And so let's walk through what happens when you do a column store join. Step 1. Oh no, let's draw it as a query plan. They come from the other side. Let's say that I have sales and I'm joining with customer. So the first thing I do, let's say my join looks like this. Select foo from sales, join I'm looking for customer. I'm looking for, let's make it more specific. Let's say that I'm looking for all customers who live in Malmö. Sorry. So here's your customer dimension, which you can't see because the colors don't work. Here's your customer dimension. The first step is we have to build a hash table on all the customers that live in Malmö. To do that, we have different traditional relational query algebra. We seek the customers. If we have an index, we'll seek it. If not, we need to scan it. You may even have a column store index that helps you do that. But what comes out of here is all the customers who live in Malmö. So what you get here is you get city, Malmö. Right. That's basically a stream of data that comes out. That goes into a batch build. This is highly multi-threaded. A lot of threads will act on this. What you now have is a memory structure, which is a hash table that allows you to look up the key of every customer that lives in Malmö. So basically it's a mapping between, what we have now is something that looks approximately like this. So let's say you have a list of, you basically have a list like that, right? These are all the customers that live in Malmö. There's 5 of those here. So that's what's happening in the background. That goes into a batch join. It's called batch. It's basically what it looks like in a query plan is just this hash join. And if you go in here and do the mouse over, it'll say batch hash join. Down here is the fact table. That's the big one. That's the one that has a column store. That goes in here. It needs to be joined here. So we basically run through all of the columns that we're interested in. Let's say we want foo from over here. So out of here comes foo. And all of the foos now get joined with the customers in Malmö in order to discover if they live in Malmö or not. Because at this point we don't know whether the foo that comes out of here lives in Malmö. That's this row. That could be in Malmö. We don't know about that. We'll have to execute the join to do it. And out of here comes then the result we need. So what happens? This is where the magic happens. Let's say that this is a very long list. This is only a snapshot. Let's say that 90% of that table of those customers are customer 42. And 10% are, let's say, 43 up to 1 million. Bad example. Not that many people in Malmö, but yeah. So that's the distribution of the table. A typical distribution of something that has some sort of favorite thing in there. Now, in order to do this join, we need to keep this table in memory. If we can't keep it in memory, you get an error, you get a little warning here, and you go fall into row mode and you get slow. So let's assume it fits in memory. There's two ways it can be in memory. It can be in level 2 caches, and it can be in main memory. If it's in main memory, it's slower than in level 2 cache, 100 times approximately. If I come out of here with a good fat stream of rows, and 90% of those are 42, the chances of me, when I look at a new 42, that the 42 was seen before. Remember, a CPU can't see anything that's not in the level 2 cache. So the hierarchy looks like this. You got the I/O coming here. That doesn't happen because it fits in memory. You got the RAM here. And you got the level 2 cache here. And here's the CPU looking at the level 2 cache. The CPU can't look at anything that's not there. So because the previous row that I saw was 42, there's a good chance that it was, because most of them are. There's a really good chance it's there in that cache. So the CPU doesn't have to go out and figure out if 42 is in memory or not, because it already knows that it's in level 2 cache. If I then get one of the other ones, let's say that I get 43, because all of my 42s are going through here all the time and all my level 2 caches are being filled up with fact rows, chances are, think of the level 2 cache like a buffer pool inside the machine. Chances are that 43 isn't there. So when I see 43, I probably have to go out and get 43 from here. That cost me 100x. Exactly. Same idea. So it therefore follows that if these ones are completely randomly distributed, and this table is larger than fits level 2 cache, and level 2 caches are what, 32 megs or something today, it's easily perceivable that hash table, I mean, there are many dimensions that are more than 32 megs. Then what happens here is that we constantly have to go here instead of going here. Yeah. And that's why skewed distributions are faster.
Then of course, it uses hashing. Yeah. So, I mean, if you have some numbers, 1, 2, and then another very common number is 1,000,000,
yeah,
then hashing solves that problem, so it will fit in the level 2 cache.
It will use hash area, but you still can't guarantee that they will squeeze in there. But yeah.
Hashing, it's okay, 100 values are used in this range of 1,000,000 values.
Yeah.
Will reduce the size because of the hash table.
Yes, this table will never be bigger than the amount of values you're interested in, right? It will only be the ones you're interested in. Yeah. Now, something else happens that's.
So it's a combination of course, skewed data plus the random, the most often run query to have the data on the level 2 cache.
Chances are that another query won't have your cache populated, because level 2 caches operate so fast that they typically only the query you're currently running, that's currently on the scheduler, has a chance of getting it done. The moment you switch to a scheduler, the level 2 cache gets purged, the new CPU comes in, wants its data. So because of the time that it takes to switch, this is so much faster than the time to go down here, right? So this is about 10 to the power of 8 slower going out there, right? So that's what happens. Now there's a few other interesting things that happen here actually. We do, any of you familiar with what a bitmap filter pushdown is? Bitmap filter pushdown. I think it's, let me see if I can find a query plan for you guys. That's probably easier. I'll show you what happens. By the way, a little thing, when you take a query plan that has a hash join in, a batch join in it from SQL 12, and you try to open in Management Studio that's older than SQL 12, you get an error. Because there's new things in there that they don't know how to render. Fast join SQL plan, that sounds right. Yeah. Yeah, I got a batch plan here. I'll explore it with you. Let's just unmute this one. Let me show you this. So here's a query plan. That's a classic old-fashioned join, right? Here's our fact table, and here it gets column store index scanned. The first thing to notice is, I think this should be an actual plan. It is. It estimated that it could do this in batch, and the estimation builds on the fact that it believes it will fit in memory on the hash tables. So it says all those hash joins that happen up here will probably be okay. So I estimate that it's batch. If that turns out to not be the case, you'll get the actual to be row. But the actual in this case is batch. All is good. Life is good. So this is actually a very fast plan. This plan plows through 700 million rows, doing all of these joins in a little less than a second. It's fast. It's really, really fast, right? So it's the kind of thing where you just, when it works, you just go, wow. Now there's a few things to notice here.
What kind of machine do you run this?
Oh, okay, this is a 40 core machine. But I'm forcing it up to 16. This could be a blade, right?
When you say fast, it was to find the kind of
Yeah,
hardware you
yeah. But this could be. Now, there's a few things to be aware of when you look at a column store plan. Some things that just go, The first one is, remember I told you this thing about throwing the rows back and forth across the machine? That's what that one does. So the first question here, of course, should be, why is it then there? Because it's not supposed to be there. This is, in case we fall into row mode, we can do this still. So this is the emergency. This is our bailout solution. If we fall into row mode, we will need to do this redistribution, and we have to change to the old strategies instead of the new strategy, which is much slower than this one. But we're not falling into row mode. And when we're not falling into row mode, notice what happens. Nothing goes through this operator. It becomes a no operator. So even though this operator's in the plan, it doesn't actually do anything. And that's sort of gotcha. Wait a minute, that wasn't supposed to happen. Here you see the dimensions. In this case, they are being accessed as in row mode. That's fine, it's a dimension, it's small, we don't care. You see up here, we did something else that's interesting. By the way, very often these index hints won't help you when you're in a column store. Some of them are just silly.
And sometimes when you create those, you get more.
Notice this one. This is a market segment. This is an interesting one. Market segment in this case is actually a pretty large table. Let me just show you. So, okay. The row scan is actually being reduced quite a lot here. But this is the market segment. We actually have a column store in this. So we're scanning the column store in row mode because this dimension is very wide. We don't know which columns we need. If we were to index this particular table, it would just be a lot of trouble. We'd have to put indexes on a lot of columns. So in this case, we don't know which columns you want. Put a column store on all of it. So even dimensions benefit from it. So this one actually is faster because of that. I think I may even have. Let's see. Yeah, here's another one. Notice here's another dimension that has a column store, and that one is also in batch. So actually, the dimension scan is now in batch mode too. So this is a larger dimension. This one gets scanned. You can see the estimated here is actually 1 million rows. So this is a 1 million dimension row join that it does here, but it uses the column store to scan the dimension and join it to the fact. So that's another interesting thing you can do about that. And again, we have this 0 thing coming here. So just notice they will be there, but they're only there if you go into row mode. So what else can we say about this interesting one? Oh yeah. Here's something very cute. We're almost done, aren't we? Yeah.
Yes.
We do something smart with the column store. When you come into the column store and the dimension keys come in, we'll have a list of dimension keys that we know we need to find. What we do is we calculate a hash on those dimension keys, and that hash we push into the fact scan. So when we run through the rows down here, the columns, we basically apply a bitmap filter directly to the column and say, could we potentially be interested in this row? If we know we don't want it, don't even send it here. This is what you see happens here, this predicate here. You see that probe here? probe opt bitmap, that one, that basically says, don't even bother joining it if we know that it won't match what we're needing. So we're basically sort of heuristically scanning the fact. And this actually reduces the row count quite a lot. So all of these bitmaps, because this is a very selective query, there's 700 million rows here, but look what actually comes out. It's very selective. Because combining all these joins with each other, we end up with 23 rows out of this particular table. So yeah, that was a bit of everything really we talked about today. But I'll be here for questions and
Yeah.
thanks.
Great.